Today there must be some plot because you have a Belgian organizer, a Belgian speaker, and a Belgian chairman. So, so it's a pleasure to introduce Stefaan Vaes from KU Leuven on negative curvature and rigidity for von Neumann algebras.
Thank you very much. So it's a great pleasure to be back in Cambridge and give this lecture on von Neumann algebras, where I will highlight several applications of the usage of negative curvature over the last 10-15 years. So I will not give you any kind of new results on negative curvature, but rather how they are used in our area to prove rigidity theorems for von Neumann algebras. Now, let me start on a very general level and try to explain you what the kind of rigidity is that we are after. So let me start with this very philosophical kind of remark. So there are two types of rigidity that we are looking at. So the very first and extremely general statement is that you're looking to mathematical structures where you try to show that some kind of weak isomorphism automatically implies a much more strong type of isomorphism, and I will concretize that in a minute. And secondly, a bit on the same level, we are looking at results where a very coarse kind of knowledge of an object gives you automatically knowledge on a much finer level. Now, we are all familiar with that type of phenomenon, for instance, in geometric group theory, to look on the one hand at quasi-isometry as, say, some kind of very coarse equivalence between groups, or on the other hand, a very strong type of equivalence, namely virtual isomorphism. Or on a similar level, more geometrically, the distinction between homotopy equivalence as a kind of coarse thing and homeomorphism on a much finer level. Now, our area in which we are looking at this type of rigidity will be in the theme of von Neumann algebras, and I will immediately give you a very brief introduction. And the two main things that we will be looking at will be the core structure would be a von Neumann algebra, for instance, around a discrete group. I will explain you how every discrete group gives rise to a group von Neumann algebra. And similarly, we will see how group actions give rise to cross-product von Neumann algebras. And then the coarse equivalence or the weak isomorphism would be isomorphism of these von Neumann algebras. And then the main question is how much can be retrieved from the much finer structure, the group or its action on probability spaces, out of this coarse data. Now, the basic method, and I will try to use all the three words because I liked the title of the conference. So there will be deformation, there will be quasi something, and there will be approximation in the talk. So the method to establish these results is Sorin Popa's deformation rigidity theory. And just to already give you a first glimpse why this kind of undertaking is non-trivial, as I will explain, namely, whenever you are in an amenable world, we will see that typically all the initial data is wiped out when you go to this more core structure. Okay, so I will show you how to use negative curvature phenomena to establish this type of rigidity results. But let me first of all give you a very brief introduction to von Neumann algebras. So what are von Neumann algebras? Just if you've never heard of that, a von Neumann algebra is a weakly closed algebra of operators on a Hilbert space, also closed under taking Hermitian adjoint. So these are star algebras. And so that's the abstract definition. And the weak topology, well, as you know, operators are said to converge weakly if they converge after applying them to vectors on the Hilbert space. Now, one of the two main examples that we will be looking at are group von Neumann algebras, and then later the cross-product von Neumann algebras. So the group von Neumann algebra is a very functorial construction due to Murray and von Neumann, associated with a left regular representation of a group. So any countable group is represented on L2 of gamma in this way, where delta of H is the standard basis vector in H. And then, how do you construct a von Neumann algebra out of this? Well, first of all, you take the linear span of these unitary operators. That gives you a realization of the group algebra, the complex group algebra. And then the weak closure of this group algebra, or the strong closure if you prefer, that gives you the same result, is a von Neumann algebra denoted L gamma and called the group von Neumann algebra. Now here is already a first question and a first phenomenon. Well, the type of rigidity question that we are looking at is how much of information on gamma can we retrieve from this ambient von Neumann algebra. Now this is quite non-trivial because, for instance, by the celebrated theorem of Alain Kohn from the 1970s, if I take as an input an amenable group that has infinite conjugacy classes, so that's the abbreviation ICC, so sufficiently non-abelian amenable group, then you always get one and the same von Neumann algebra out of it. So there is a kind of wiping out of structure that's happening while taking this weak closure. Because very famously, it's really in taking the weak closure that the structure is wiped out, because there is the famous conjecture, at least when gamma is torsion-free, that it might be possible for all torsion-free groups to recover gamma just from this star algebra. So it's really in the weak closure kind of operation that the structure goes away. Now, on the other hand, it's not so that all information is wiped out. No. I mean, on a more qualitative level, it has been known for quite a while that many group-like properties are actually invariance properties of the ambient von Neumann algebra. Amenability is like that, property T is like that, the Heurup approximation property that we will meet later is of that type. All these are actually invariants of the von Neumann algebra, yeah? So there are ways to distinguish between von Neumann algebras. Okay. So let me already right away go into a result that I can state with this one slide of knowledge on von Neumann algebras and illustrates already usage of negative curvature. So I need two lines of terminology. First, in this kind of context, it's quite useful to restrict our attention to a specific class of von Neumann algebras called 2-1 factors. So what are 2-1 factors? These are von Neumann algebras that have a trivial center and that admit a tracial state. So it's a functional on the algebra that behaves like the trace on matrices. Now, for our purposes, this is absolutely no problem, because indeed, these group von Neumann algebras, they are 2-1 factors, at least when you assume that the conjugacy classes are infinite, so as to exclude a center in the algebra. Okay. So here is Ozawa's theorem from 2003. And at first sight, I'm sure that it will not look very impressive, but I will try to explain you why this was a huge breakthrough and how to deduce true structural results on 2-1 factors from it. So what Ozawa proved is that whenever you take a hyperbolic group that is ICC, then this associated 2-1 factor has a very special property that he coined solidity. So what is in general the definition, this structural property that happens? Well, before reading this line, what it will boil down to is that in this 2-1 factor, there is not a lot of room to commute, as you expect from a hyperbolic group. Yeah? In a hyperbolic group, there is not much commutation happening. Well, the same here, the perfect statement that Taka made is that whenever you have a subalgebra which is not locally trivial, and I will say in a minute what is locally trivial, then the elements that commute with it must be amenable. Now, read this as the quite trivial group theoretic statement that in a hyperbolic group, the centralizer of an infinite subgroup would be an amenable subgroup, yeah? And even much more strict, of course, in hyperbolic groups. Okay, so what is this notation? So this A prime intersection M is called relative commutant, or elements in M, all x in M that commute with everything in A, so it's like the centralizer. And locally trivial means that an algebra would be called locally trivial if it admits somewhere a minimal projection. So this amounts to saying that there is somewhere a projection in A such that actually under that projection the algebra is actually the complex numbers. And then, of course, you cannot expect anything like this because everything would commute with complex numbers, yeah? Okay. So these are, this is an obvious assumption to make. Okay, now here is already a first real structural consequence of this result, and that was quite amazing already at that time. Namely, it follows that these von Neumann algebras that come with hyperbolic groups, that they are so-called prime. It means that they cannot be written in a non-trivial way as a tensor product of von Neumann algebras. Now I must say in a non-trivial way, because 2-1 factors you can always write them as 2 by 2 matrices over something else or n by n matrices over something else. So meaning non-trivial with both M1 and M2 infinite dimensional, yeah? That's the true thing. And what is this type of tensor product? Well, it's really tensor product of von Neumann algebras. That's why we put the bar on top of it. But to keep in mind, I mean, it behaves well with taking direct products of groups, yeah? So with group von Neumann algebras, it amounts to doing this operation. So this shows that that the group von Neumann algebras of hyperbolic groups have this kind of strong indecomposability property. But there will be more striking consequences in a minute. Now, why hyperbolic groups? So why could Ozawa prove this for hyperbolic groups, and how did he do that? Well, that's because there is actually a much more conceptual class of groups behind. And that's what he coined at a certain point, class S. And what is class S? So class S of Ozawa is the following. A countable group is said to be in class S if you have the following phenomenon. We have to look at the left-right action of gamma on itself. So we have the group gamma. The first gamma is acting by left multiplication. The second gamma is also acting by right multiplication. Now the assumption is that this action can be compactified to an action on a compact space, so containing gamma densely, so that it becomes an action by homeomorphisms. Okay, that's nothing. You could take kind of Stone-Church compactification. But then there is an assumption. And the two assumptions to make are, first of all, that the action on the right multiplication action, should become the identity on the boundary. So it's a compactification, so you get a boundary, and the action by right multiplication should become trivial on the boundary, while the action by left multiplication, it's a completely different phenomenon. The action by left multiplication should, on the compact K, become what is called a topologically amenable action, and in a minute I will tell you what is an amenable action. So it's really, that's what he considered, and it's for this class of groups that he could prove his theorem. And of course, what's the relation with hyperbolic groups? And that's really the prototype of compactification that you should keep in mind. If gamma is a Gromov hyperbolic group with its Gromov boundary, then really that's the type of action that satisfies these two properties. Because indeed, well, let me first tell you in a minute what is amenability. So amenability of an action, topological amenability of gamma acting on K. It really means that there exists a sequence of maps from K to, say, probability measures on gamma that is more and more equivariant. And I will not write it in a precise way because that would take too much time. But it's as n goes to infinity, asymptotically, this is more and more like this, yeah? Okay, and then we say that the action is topologically amenable. Okay, why does this happen with the left action of a group with the action on such a boundary? Well, it's very easy to see how to have this kind of psi n when you take the free group. So if you have the free group, you take its Cayley graph, you have the boundary at infinity, and then what would you do? Given, how would you construct psi n? Well, given a point at infinity, you would look at the infinite geodesic that goes, say, from the neutral element to your point at infinity. And of course, you cannot take a uniform probability on this infinite geodesic, but you can cut it off at the first n elements and let the n tend to infinity. Yeah? And then you get this approximate equivariance. So it's really this kind of negative curvature, in this case even for tree phenomenon, that you can mimic even for hyperbolic groups, and that shows you that this boundary action is amenable if gamma is hyperbolic. And of course, if you took the boundary in this way, like the boundary of the Cayley graph, then you indeed see that the action by right multiplication disappears if you tend to infinity. Yeah? Because then if you write a longer and longer and longer word, action on the right is doing nothing anymore. Yeah? Okay. Good. So that is this class S for which Taka could prove his theorem, and the negative curvature is hidden in the proof of the amenability of this boundary action. Okay, but the negative curvature also comes up in another way, because this class S, coined in terms of amenable actions, can be also formulated in a quasi manner, and now the quasi will appear for the first time, because what Ozawa also proved is that the group is in this class S, so in terms of having such kind of boundary action, if and only if, first there is, I would call this a technical condition, gamma is exact. I mean, every reasonable group one encounters in life is exact, so, and huge classes are known to be exact, so you may very well ignore this condition that is, say, always satisfied. But then secondly, and that's the true condition about being in class S, there should be something that vaguely resembles, as I will explain, a proper co-cycle from gamma to L to gamma, something that is familiar to you, but it's only in a very weak way, in the sense that there should be a proper map from gamma to L to gamma, such that you have this kind of almost equivariance, in the sense that for a fixed G in gamma, the supremum of all these differences should stay bounded if H runs through the group. Now, a way to satisfy this is, of course, if you have the following stronger property, if you have a quasi-cocycle. So what would be a quasi-cocycle? A quasi-cocycle would be a map from gamma to L to gamma, such that the cocycle identity may fail, but the defect with which it fails is bounded over all G and H. Yeah? So, of course, if you have this, then you can make the estimate here as the defect plus the norm of CG, yeah? And then clearly we have our bound for every fixed G. So therefore you see that having this type of property, having such a proper map, is quite closely related to another thing that has been studied by Andreas Storm. So we are quite close to the world of groups that admit a non-trivial, of course here it's non-trivial, here it's proper, but okay, that admit non-trivial quasi-cocycles into the regular representation. And then, as you know, quasi-cocycles, it's like the obstruction of bounded cohomology. Well, here there should be an L2 gamma. So we are also very close now to the world of groups in the class of Monod and Shalom, where the second bounded cohomology is non-trivial. So you see these are all quite closely related, with indeed non-elementary hyperbolic groups being the primary examples of each of the three classes, of course. Yeah. Okay. So in that way, the, say, quasi-cocycles, or more generally, this kind of maps were used by Ozawa to establish this, at first sight, maybe strange solidity property for group von Neumann algebras. Okay. But let me maybe show you a few more striking structural properties that could be deduced using these methods. So here is just a quick reminder that was Ozawa's theorem, or a consequence of it, that if gamma is non-amenable and in class S, then the group von Neumann algebra is prime. It cannot be decomposed as a tensor product. But then Ozawa and Popa could show that not only these algebras are prime, but also that there is a kind of unique prime factorization theorem. So the unique prime factorization theorem that they could show is that if you have a whole bunch of groups in this class S, say hyperbolic groups, and if their direct products happen to have isomorphic group von Neumann algebras, then the only way that this can happen is because there were the same number of groups at both sides, and after a certain reshuffling, and here of course you would have preferred to see L of gamma I isomorphic with L of lambda I simply, but there is a little nuance, because in 2-1 factors we have a lot of flexibility, and for instance, in 2-1 factor theory, we can take m to the n, that would be n by n matrices over m. And then m to the t makes sense for all t positive. So that's the nice thing. The nice phenomenon of continuous dimension makes that you can interpolate between all these n by n matrices over a 2-1 factor, and then you have this kind of phenomenon that if I make a tensor product of an algebra to the power t with another algebra to the power 1 over t, that this is canonically. So this is, of course, something you cannot really do with matrices because one of the here will be smaller than 1. But that type of formula is canonically true, and therefore, so the product of the ti's would be 1. So that kind of phenomenon can really happen, actually. Okay. So this is already this kind of rigidity theorem in the spirit of the first slide, because we only get as an input isomorphism of ambient von Neumann algebras, and as an output we know something on the group, but something rather modest, the number of factors. But then much more recently, Stefaan, De Santiago, and Thomas Sinclair, they could prove the following amazing statement. Take non-elementary hyperbolic groups that are ICC and assume that the group von Neumann algebra of their product can be realized by any other group. I don't make any assumption on lambda. Well, then I can deduce something about lambda. Not so much, but something. It must be so that also lambda is a direct product of n groups, which is quite amazing that you can just get it out of this very coarse data at the start, and then again you can do it in the way of Ozawa Popa with each of the factors corresponding to each other and with the product of these exponents being 1 then, yeah? Okay. Now, as you noticed, here I had the nice statement with the abstract class S, while here I specify to hyperbolic groups, and indeed I've been cheating a little bit in the presentation because there goes much more technology improving this than there went technology improving Ozawa Popa's theorem, and indeed it's not known whether this last statement holds for all groups in class S, and so we will see later that there is a bit more input needed, yeah? Yes?
You did assume something about lambda in the first theorem and did not.
Here I make no assumption at all.
But do you get a conclusion about lambda is something?
Yes, that lambda must also be decomposed as a product of n.
But is it in class S eventually?
Lambda is.
Lambda is?
A posteriori, yes. Yeah. So, but a priori you don't know. Yeah. Okay. So here maybe that's good to say. Of course, I will start discussing on the next slide cross products, but those who are familiar with measure equivalence of groups will recognize this type of phenomenology, yeah, where if you have a direct product of hyperbolic groups, measure equivalent with another group, then there also such kind of splitting happens. But this is of a really different nature. Okay, let's go to cross products. So what are these cross products about? So the input data is a countable group acting on a probability space, preserving the probability measure. And with that, again, I build your von Neumann algebra in the spirit as building a group von Neumann algebra. Okay, so this cross product is generated by, on the one hand, a copy of L infinity of x, and on the other hand, a copy of the group von Neumann algebra, so generated by unitary operators UG. Then the finite sums of elements in A and the unitaries UG, they form a dense star subalgebra, and the product in this algebra is, of course, given by how gamma is acting on x. So if I take an elementary term like this and I multiply, then it's like in a semi-direct product. This is the only thing I can do. And there is a trace, because the action was preserving the probability mu. There is a trace, and the trace is by just integrating the coefficient of the neutral element in the group. Okay. So of course, group von Neumann algebras are a special case, because if there wouldn't be an x, then I just found back L of gamma. And if you want to keep in mind a huge supply of examples, there have been lots and lots of articles and works about Bernoulli actions and their cross products. But also, I mean, there are a lot of very interesting things for this type of algebraic actions, groups acting by automorphisms of compact groups. Yeah. Okay, so that's the group measure space construction of Murray and von Neumann. Now, before going into rigidity theorems for these von Neumann algebras, I need a little bit more of terminology. So let me first focus on when you get a 2-1 factor. So how to make sure that there is no center. Well, the usual assumptions are to absolutely not take the trivial action. We will assume that the actions are free, or at least essentially free. So for almost every point in X, there is a trivial stabilizer. And we will assume ergodicity. So there are no functions on X that are gamma invariant, except constant functions almost everywhere. And under these assumptions, not only you get a 2-1 factor as a cross product, but this 2-1 factor now comes with a favorite subalgebra, namely L infinity of X. And this favorite subalgebra plays a very special role. So it's called a Cartan subalgebra, not the best terminology that has been chosen, but that's the way they call it. I think Dixmier called it like that. So it's a Cartan subalgebra, meaning that it has the following abstract properties. So what is a Cartan subalgebra in a 2-1 factor? A Cartan subalgebra in a 2-1 factor, it's a subalgebra that's maximal abelian. So anything in M commuting with A must be in A. And such that its so-called normalizer, namely the unitary operators that normalize the subalgebra, must generate M. It's a bit like having a maximal abelian normal subgroup, but only a tiny little bit like having that. Yeah. Okay. Now, why is this concept so crucial? Well, the theorem of Ising-Singer is the following, namely, if you look not only at the 2-1 factor, but the inclusion of A in the cross product, this inclusion contains exactly the same data, and I will explain to you what I mean by this statement, contains exactly the same data as the so-called orbit equivalence relation. So with the action of the group on a probability space comes an equivalence relation, namely the partition into orbits, this equivalence relation here. And the point is the following. First of all, the cross product, although I defined it on the previous slide in terms of really the action, you can actually construct it from the equivalence relation. So with any equivalence relation comes this type of cross product. So indeed, the cross product as a 2-1 factor containing A only depends on the equivalence relation. But also conversely, you can recover this equivalence relation from the inclusion. So therefore, the inclusion, giving the inclusion is exactly the same as giving the equivalence relation. Okay. Therefore, there comes this important question immediately in front of you, namely, what can we say about existence and uniqueness of Cartan subalgebras? Because if you can come up with a context where 2-1 factors have a unique Cartan subalgebra, then you have a rigidity statement. Then you recover the equivalence relation as an invariant of your ambient 2-1 factor. So we will look at this problem of uniqueness of Cartan subalgebras and see that again there is a big role played by negative curvature. Okay. So the very first result in this direction has nothing to do with negative curvature. It was Voiculescu who proved that the free group factors have no Cartan subalgebra. And his method was in really a different field. He used a lot of free probability theory to prove that. And some of this should not come as a surprise. I mean, if you think at the free group, you absolutely don't have anything abelian that is vaguely normal inside. Yeah, you don't expect to have this, but to push it up to the von Neumann algebra level is much, much harder. Okay. Now, at a certain point, when Ozawa proved this solidity theorem, of course, you would say in a hyperbolic group also you cannot have such an abelian part that's normalized by a lot of things. So maybe hyperbolic groups should also not give you Cartan subalgebras, and maybe even his class S, because that was ultimately what he showed, that for class S you had solidity. Well, no. I mean, people tried for a while, but then Ozawa came up with an example, namely this group, which we would not consider as negatively curved, nevertheless is in this class S. So the class S is a bit strange at the same time. So this semi-direct product sits in class S, and of course if you take its group von Neumann algebra, it contains the group von Neumann algebra of Zito, so L infinity of the 2 torus, as a Cartan subalgebra. So class S is not enough to prove absence of Cartan subalgebra. It's not enough to prove uniqueness of Cartan subalgebra for cross products. So you need something extra. And there was quite a quest for that until Ozawa and Popa managed to do it. So what they could prove is that if you take a non-amenable group, and now let's take something that's closer to negative curvature than just class S, and always suppose that we have a proper cocycle into L2. Okay, like the free groups have. Assume that we have a proper cocycle into L2. But then we still need something extra, and that I will explain to you. There will be an approximation property needed called the complete metric approximation property of Heuerup. And under these two conditions together, they could show that L of gamma is no Cartan subalgebra, and they could prove uniqueness results for Cartan subalgebra, namely, and I will also explain you that notion, if you take an action that's profinite, then the cross product has a unique Cartan subalgebra, namely L infinity of x itself, up to unitary conjugacy. So now there are quite a few things that I have to explain to you. I will go a bit into the complete metric approximation property and its relation to other approximation properties for groups. I will say a few words about profinite actions and why profinite actions here, and give an idea how they could do that by saying, it even says non-trivial things about groups. So that will allow me to express the basic idea of their proof. Okay. So this is again what Ozawa and Popa proved. And let me explain to you this complete metric approximation property. So what is the complete metric approximation property saying? Well, I have first to tell you what is a Fourier multiplier on a countable group. So Fourier multiplier on a group gamma, that's a map from, it's a function on gamma. And with the function on gamma comes a multiplier. It's like multiplying the Fourier transform and then transforming back, yeah? It's a map from the group von Neumann algebra to itself, where the basic unitary UG is just multiplied by phi of g. Now what you ask is that this, to be a Fourier multiplier, you request that this map is bounded in operator norm. But not just bounded in operator norm, it remains bounded with bounded constant if you apply it to 2 by 2 matrices, 3 by 3 matrices, n by n matrices over L of gamma, the notion that is coined completely bounded. Okay, why is this a useful notion? Well, it's a generalization of a positive definite function. So what are positive definite functions compared to Fourier multipliers? Positive definite functions are exactly the Fourier multipliers where this completely bounded norm that appears as the completely bounded norm of this multiplier is just the least it has to be, namely the evaluation in the neutral element. So that's a way to characterize positive definite functions. Okay. This means that we come close to a characterization of amenability. So as you know, one way to characterize amenability is to say that you can approximate the identity by finitely supported positive definite functions. So what is the complete metric approximation property? The complete metric approximation property, CMAP, means that we can approximate the identity by finitely supported Fourier multipliers. And then we have to, of course, impose the bound that the CB norm, the completely bounded norm, is not exploding. Let me right away, for later use, add the notion of weak amenability. So weak amenability is exactly the same. You can approximate the identity by Fourier multipliers, finitely supported, but now these CB norms need not converge to 1, but just have to remain uniformly bounded. Okay. So, CMAP, weak amenability are really generalizations of amenability. I will go deeper into which groups satisfy these approximation properties, but for now you can just keep in mind that the free groups do satisfy this. So that was what Heuerup proved. So that was one thing. I had to explain the CMAP, and let me now say 2 words about what are profinite actions and how they are used. Well, so profinite actions is nothing else than inverse limits of actions on finite sets. So if you want to take them ergodic, then it's really like taking a decreasing family of finite index subgroups, and you make gamma act on the inverse limit of the gamma mod gamma n, yeah, with a normalized counting measure. Okay, so this is a very nice class of group actions. Now, why did this come into the picture? Well, if gamma has the complete metric approximation property and the action is profinite, then the cross product, because keeps the complete metric approximation property, because this approximation property, it's again actually an invariant of the 2-1 factor. And you can lift it to the 2-1 factor when the action is profinite, but otherwise not. Now, this is of course very vague, but I will show you in a minute a group theoretic statement. What Ozawa and Popa discovered is that if you have a 2-1 factor with this complete metric approximation property, and if you take any subalgebra that is amenable, then something happens. Now, what is this something? Well, this something can be illustrated on groups. And this solved a conjecture that I will talk about in a minute due to Michael Cowling. So what Ozawa proved is if G is a weakly amenable group, in particular if you have a group with a complete metric approximation property, then this imposes something on its normal amenable subgroups. So what he showed is that if you take an amenable and normal subgroup, then on this amenable and normal subgroup N, there must be an invariant mean. Well, of course there is a mean that's invariant under translation by N, because N is assumed to be amenable, but at the same time it will be invariant under conjugation by G. So that's the strong structural property that follows just from this weak amenability of the ambient group G. Okay. Now, of course, I will not go deeper into von Neumann algebras, but you can probably believe that if I now take a 2-1 factor that is weakly amenable or has this complete metric approximation property, and I take an amenable subalgebra, then for the normalizer of that subalgebra, there will be something invariant somewhere, but I have to cook up the right context. In the same way as here there is a mean on N that becomes invariant under the normalizer, yeah? Under G. Okay. Anyway, now why am I putting a focus on this group structural result? Because there was a question due to Michael Cowling that had to do with the characterization of the complete metric approximation property. So before going into that, here are a list of groups that have this complete metric approximation property. There are also stability properties. It's stable under taking direct products, free products. It's also stable under measure equivalence, by the way. Here are a few weakly amenable groups. So lattices in SPN1, hyperbolic groups in general, stable under direct products and measure equivalence. And then, that's the main reason why I was making these lines, some advertisements. It's really not known and wide open whether weak amenability is stable under free products. So this sounds like quite an innocent statement, but it is not. Okay, now you may have the feeling already that this complete metric approximation property is closely related to another approximation property due to Uffe Heurup asking whether or not there exists a proper isometric action of gamma on some Hilbert space. Equivalently, there is a proper 1 cocycle into some unitary representation. Now, the conjecture of Michael Cowling was that the Heurup property is the same as the complete metric approximation property. Now, that was negated in one direction by a combination of works. These are not initials, these are, so it's Cornulier, Stalder, Valette, Ozawa, Popa. Namely, and I will say how to combine their works, if you take the Reed product of the group with 2 elements and the free group F2, what you get in that way is a group with a Heurup property. Why? Because Cornulier, Stalder, Valette proved that the Heurup property is stable under taking Reed products. So the Reed product of this finite even group and Heurup group gives you a Heurup group. But then, what did Ozawa and Popa prove? That on an amenable normal subgroup, namely this infinite product of Z over 2Z, there must be a G invariant mean, which would force a amenability of F2, and therefore this is not the case. Now, also the other direction remains open. So I don't think people believe that it could be true, but there is no example of a group with C map and not the Heurup property. Okay, so that was the digression, because all this was into the conditions of the uniqueness theorem of Ozawa and Popa. But then it got improved. So Stefaan and Thomas Sinclair could get away with only class S, so no need for a proper one-core cycle, and they could get away with weak amenability, no need for the complete metric approximation property. And still the same conclusions. L of gamma has no Cartan, and if you take any cross product with a profinite action, the Cartan subalgebra is unique, therefore the equivalence relation is an invariant of the 2-1 factor. Okay, so why was this quite important? Now we do cover again all hyperbolic groups, because we have already seen that hyperbolic groups are in class S, but also hyperbolic groups are weakly amenable. So that was proven by Ozawa again. Okay. Now, still profiniteness is used in exactly the same way as in the Ozawa-Popa proof, namely because of profiniteness and the fact that gamma is weakly amenable, the cross product is weakly amenable, because again weak amenability is actually an invariant, a property of the ambient 2-1 factor. And that could then be removed as a condition in work that Sorin Popa and myself did a few years back now, namely exactly the same result holds, but actually it holds for arbitrary actions. There is no need to just look at profinite actions. No, uniqueness of Cartan holds for arbitrary, free ergodic, and probability measure preserving actions. So how could we do that? Of course, I will not go into that, but it's really because all this weak amenability and approximation stuff has to be in the correct way relativized to L infinity of x, because on L infinity of x you cannot assume anything. The action could be a Bernoulli action, like the furthest one can be away from profiniteness, and so on. Okay, so maybe this, let me show you very quickly a corollary. So this is a very neat, I would say, classification or rigidity statement that follows from it. If you take two cross products with free groups, arbitrary free and ergodic probability preserving actions of the free groups, then if their cross products happen to be isomorphic, so that's the coarse type of equivalence, then you know something more. Then the number of generators for the free groups must be the same on both sides. So why does this follow? Just to give you a flavor of that type of reasoning. Indeed, if there is such an isomorphism, since we know that there is uniqueness of Cartan subalgebras, you can choose an isomorphism that maps L infinity of x onto L infinity of y. So it's an isomorphism that preserves the inclusions. As I said, that's exactly the same as preserving the equivalence relations, the orbit equivalence relations. So this means that it induces an orbit equivalence of the actions. So what's an orbit equivalence of the actions? It's an isomorphism between the spaces that sends orbits onto orbits almost everywhere. But then you can go into orbit equivalence theory, and in this case it's the work of Gaboriau that can help you, because Gaboriau introduced several invariants for equivalence relations, most notably cost or L2 Betty numbers. Both would work in this case. So the cost of this equivalence relation is n. The first L2 Betty number is n minus 1. So you can use this to recover the n from the equivalence relation. Of course, needless to say, I mean, this is really about cross products. So it's wide open whether the free group factors are isomorphic or not. Okay, maybe to conclude the discussion about uniqueness of Cartan, let me introduce a terminology. I will call a group Cartan rigid, so this is really a property of a group. I will call a group Cartan rigid if for any free and ergodic action the cross product has a unique Cartan subalgebra up to unitary conjugacy. So this Cartan rigidity holds for quite a few groups, but at the same time it's open for an even larger class of groups. Namely, just to summarize the theorem that Sorin and I proved, it holds for weakly amenable groups in class S, so in particular for hyperbolic groups. And then Adrian Ioana could prove that it holds for arbitrary free products, at least when the free product is not amenable, so not Z2 free product Z2. And then, as such, Cartan rigidity is not stable under any kind of property, but there is a technical strengthening that one can formulate for that is slightly stronger than Cartan rigidity, and that natural strengthening, of course, holds for all these classes, and that is stable under extensions and under a few other operations. Now, in principle, but of course this is, I should not say this to a von Neumann algebra audience, but maybe here I can say it like this. In principle, if you want some work to do, any group property that you would come up with, and that excludes in a very strong way, to have anything vaguely normal abelian or vaguely normal amenable, might be a property that implies Cartan rigidity. But you will have to work, because it's wide open whether the SLNZ, for which we do know this type of thing, yeah, whether the SLNZ are Cartan rigid if n is at least 3, yeah. I would consider this as really a nice breakthrough if somebody could prove. I mean, for sure these are Cartan rigid, yeah, but we have no clue for the moment. Okay, let me go in the remaining 5 or 10 minutes that I will take into a more recent thing. Actually, many of these things can be done for locally compact groups. And this gives rise to a completely new type of von Neumann algebras. So, of course, already in the work of Cowling and Hoyerup, weak amenability, it goes through like this immediately for locally compact groups. Ozawa's class S is perfectly well defined for locally compact groups. There are, of course, the first and obvious examples are the rank 1 connected simple Lie groups. And then you come into a new class of groups that is really different from the countable groups that we were looking at so far, because here you could still connect them to their lattices and so on. But namely closed subgroups of the automorphism groups of trees. So every locally compact group that acts properly discontinuously on a tree or on a hyperbolic graph will be weakly amenable and in this class S. So this is a huge family of groups that you know more about than I do. Now, what we could prove just earlier this year with my student Tobe Dupré and former postdoc Arnaud Brottier is that if you take any of these locally compact groups, then still you can perform cross products, and I will now state it in a completely general way. So I will not even assume that we look at actions that preserve the probability. These groups typically also have many actions that are just non-singular, that preserve sets of measure 0. So you take any free energodic and non-singular action of any of these locally compact groups, then, well, of course, you would now like to see appear the conclusion that the cross product has a unique Cartan subalgebra. But first of all, the cross product could be amenable, and then it has by no means a unique Cartan subalgebra. And because there is no invariant probability measure, this can really happen, even when G is non-amenable. So one thing that could happen is that I took here something like a boundary action, that I took an amenable action in the sense of Zimmer, and then I just get one of the completely classified amenable von Neumann algebras for which there are tons of Cartan subalgebras, yeah? Or it's unique. So it's one of both that happens, yeah? If you took a non-amenable action, then you will have a unique Cartan subalgebra. Now, I have to explain you on the next slide. For those who know how to construct cross products with locally compact groups, it's not L infinity of X that is the Cartan subalgebra. No, because a Cartan subalgebra should come from a countable equivalence relation, an equivalence relation with countable equivalence classes. Now, if a locally compact group is acting somewhere, you don't see an equivalence relation with countable equivalence classes. So you have to take the so-called cross-section, which is quite known, but let me explain it nevertheless. So if you start with an action of a locally compact group on a probability space, one can pick so-called cross-sections. So what is a cross-section for the action? It means that it's like a small enough Borel subset, and at the same time large enough, small enough, so that for a neighborhood of the identity in the group, if I act with something in this neighborhood on something in x1, I always get out of x1, yeah? So the map from u times x1 into x will be injective, but at the same time x1 is small enough, it's not just 1 point or so. No, the image should not have measure 0. And that always exists. Actually, you can even take it of course not with the image being the entire of X, but you can take it with the image, of course, meeting every orbit, yeah? Okay. Then, by construction, because of this neighborhood, so with the neighborhood of the neutral element, you cannot go back from x1 to x1, so therefore, if I restrict the orbit relation to x1, there I have a countable equivalence relation, yeah? And of course, it looks as if it depends a lot on this cross-section, but up to stable isomorphism, as they call it, of equivalence relation, this does not depend on the choice, yeah? So it's really a kind of canonical thing you attach to the group action. And it's really that thing that produces the canonical Cartan and the one that is truly unique in this. It produces the Cartan, and in our theorem, it's the unique Cartan of these von Neumann algebras. Okay, maybe to give you a better feeling with the more concrete statements, here is the type of rigidity theorem you can deduce from this, and that will remind you of certain things that Monod and Shalom did before. I will make the connection in a minute. So take 4 groups in this class. So take, if you wish, closed subgroups of automorphisms of trees or something like that, so weakly amenable and in class S. And now you take free and ergodic probability measure preserving actions of their direct products. I hope that I didn't, irreducible. So this is not only an ergodic action, but each G1 and G2 should be separately ergodic, yeah? I forgot to put that, but it's absolutely crucial. Well, the theorem we prove is that if their cross products happen to be isomorphic, then the groups and the actions must be the same. So then, conclusion, there must be an isomorphism of measure spaces, there must be an isomorphism of groups, conjugating everything onto everything, yeah? Okay. Completely, so here you really recover a lot of the initial data out of the ambient von Neumann algebra. But again, irreducibility should absolutely be added. Now, what is the method? Of course, uniqueness of Cartan subalgebra, as I said, allows you to recover the equivalence relation, which is now the cross-section equivalence relation. And then you have to prove that for such irreducible actions of product groups, you can retrieve the group and the action out of the orbit equivalence relation. Now, in very similar setups, this has been done. I mean, Monod and Shalom have proven that type of statement for countable groups in their class. And as I said, class S is very closely related to that class. And also, and Sacco has proved it exactly for class S, but for countable groups. And then, of course, you can believe that it can be done for locally compact groups. But that's exactly one of the final points in the paper. Okay, that's where I will stop. Thank you.
Thank you very much. Questions, comments?
So you said that groups locally compact groups acting on trees and hyperbolic graphs are weakly amenable. What about, are there simple locally compact groups that are not weakly amenable that you know of?
For sure, because so weak amenability excludes already, I mean, all this read product kind of behavior, or even, yeah.
Okay.
Yeah.
And anything of higher rank is not weakly amenable.
Okay. I was thinking more like the Nuritin groups, if those were known.
Say it again?
The Nuritin groups, or the almost automorphism?
No, but just take SL and R. I mean, yes.
You mentioned the problem of SL and Z.
Yes.
Cartan rigidity. With the theory for locally compact groups, do you know the same for SL and R?
No, that's at least as hard. Yeah.
I mean, is it equivalent?
It's never on the nose equivalent, but it's absolutely sure if you can do one, then you can do the other. But there is not like a generic statement that would allow you to really prove that it's the same thing. But yeah.
So in the context of non-discrete locally compact groups, so very naturally you also get non-free actions, for example, G acting on G mod P or G mod gamma. So what about the theorem you proved, do you expect it to be true for non-free ergodic?
Well, there are two sides on for what you say. So about this type of result, I wouldn't be able to tell you anything because it's not with, you don't have a Cartan subalgebra and so on. But for the other one, what would follow is that if the action is not free, then the cross product simply has no Cartan subalgebra. So already something breaks down from the start, yeah. But maybe one can still recover something of this nature, but I don't know. Yeah.
Any other question? The case. So let's thank Stefaan again.